later on. Good evening, ladies and gentlemen. Welcome to the national headquarters of the Theosophical Society in America. My name is John Gianjosi. I'm the Director of Public Programs. At this time, I ask that you silence your cell phones and other noise-making electronic devices. Thank you. This evening's lecture is being streamed live, and I welcome friends watching through the internet. The Theosophical Society promotes study, meditation, and service. We encourage open-minded inquiry into the world religions, philosophy, science, and the arts. We also have a deep respect for the unity of all life. Our goal is to help people explore the spiritual path so as to arrive at a deeper understanding regarding the wisdom of the ages. And we feel this wisdom is not limited to any one tradition, thus we offer programs from various traditions. I do encourage you to take one of our program catalogs in which you'll find the programs being offered during the remaining month of February and then March. The spring-summer catalog will be coming out in about a month's time. These programs are also on our website, and there you can register for the programs that are of special interest to you. The Theosophical Society is a membership organization, and members do receive some benefits that are special to members, such as being able to attend the Thursday evening lectures free of charge, receive discounts for many of the other programs, receive a quarterly magazine, have borrowing rights from the library, and on and on. So consider joining, as there are some benefits. However, the real purpose for joining the organization is that you want to support the mission and want to help us continue to do this work. But what we offer here, very importantly, is not just for the members. It is open to the public at large. It is for the benefit of everyone, and everyone is always welcome. So I'm very happy to see you here this evening. And I am especially happy to have back one of our special presenters. Dr. Dan Hooper has spoken here on a number of occasions, and we always feel honored when he accepts our invitation to come and lecture here, because he often lectures for much more esteemed audiences than the ones we can provide here. But he is generous with his time and has agreed to come and speak here again this evening. For those of you who do not know Dan Hooper, he is a member of Fermilab's Theoretical Astrophysics Group and an associate professor of astronomy and astrophysics at the University of Chicago. His research focuses on the interface between particle physics and astrophysics, and in particular on the questions related to dark matter. He is the author of many books, including Dark Cosmos, Nature's Blueprint, and most recently, At the Edge of Time. And we do have this book available here this evening for you to look at and maybe purchase. And most fittingly, his talk this evening is based on his newest book, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. Please join me in welcoming Dr. Dan Hooper.
Thanks, everybody. It's a pleasure to be here. I haven't been back to the Theosophical Society for, 3 years or something. So I'm happy to be here and talk to you about some of the ideas that I've been writing about and thinking about in my research. So I just want to open with an expression of why I think it's so exciting to be a cosmologist right now. Throughout all of history, people of all times and cultures have looked up at the night sky. They've looked up at that sky and they've wondered about their universe and how it came to be. In this respect, we are just like any number of our ancient ancestors. But in one important way, I think we're very different. We're different because we're at a very privileged time where for the first time, when we look up at our night sky, we more or less understand what it is we're looking at. Just think about that for a second. You know, in all of human history, there's been about 100 years where we could say that was true. And we happen to be in that century. Take this image, for example. This is an image taken by the Hubble Space Telescope. It's part of the program known as the Deep Field program. Most of those blotches of light, you see, not all of them, most of them are galaxies, similar in size and shape to our own Milky Way. But because it takes time for light to travel across space, this image doesn't show what these galaxies look like today or what they are like today, but rather what they were like more than 13 billion years ago, only a few 100 million years after the Big Bang. Our universe was a very different place then. And for the most part, we understand how and why our universe has changed from the hot and dense state that we call the Big Bang into the world we find around us today. Before this gentleman, physicists didn't even have the tools to talk about how space might change or evolve, or how it might have originated. Those were questions that didn't even make sense in the grammar that physicists used. The old Newtonian paradigm of physics was one in which space was a constant static backdrop through which objects could move. But Einstein showed us that space isn't really like that at all. Space can do things, Einstein taught us. It can curve, it can warp, it can expand, it can contract, and in principle, it could begin or end. Einstein's theory of general relativity, first published in 1915, made it possible for physicists to start to ask questions about what the space that we call our universe may have been like in the past, or what it might be like in the future, and even how it might have originated. So, if you're like most people, you've heard before that our universe is expanding. But you probably don't have a good feeling for what it really means when we say space is expanding. Well, what Edwin Hubble observed in 1929, that was our first indication that space is expanding, was that all the galaxies he could image with his telescope seemed to be moving apart or away from us. And furthermore, the farther away a given galaxy was, the faster it seemed to be moving away, or faster it was moving away. What we understand this to mean today is that space is growing. The distance between any 2 points in space is getting longer or larger as time progresses. Now, I've given talks like this enough times recently to know that the bulk of you are probably asking yourself the same question right now. I know we've been asked to hold the questions to the Q&A, but I bet if you could ask a question right now, most of you would ask something along the lines of, what is the space expanding into? Show me your hand if that's, yep, okay. So it sounds like a reasonable question. If I tell you space is expanding, you want to say into what? But it's not a very good question in the sense it doesn't have a very good answer, because if there were something that space could be expanding into, what would we call that something? Space. So when a cosmologist says space is expanding, they don't mean some of space. They don't mean there's some object somewhere in space and they're growing into some, or moving into some previously unoccupied place. That's not what we mean. When we say space is expanding, we mean all of space. All of it's expanding. And that means it's not expanding into anything else. The volume of space is getting bigger, the entirety of the volume. Now, this is confusing. It's super counterintuitive. Our brains were designed by natural selection to do really well at understanding our kind of macroscopic local universe, okay? So I can understand if I throw a rock, roughly where it will go. I can understand if I jump over something, roughly where I'll land. All these sorts of intuitions we have about physics were designed so that we could, catch prey better and avoid predators and any number of other practical things. But natural selection did not help our brains to understand things like the subatomic world of the quantum or the general relativistic world of the cosmos. These are things we have to trick our brains into understanding through various kinds of techniques and training. When I was a grad student, I was really struggling with this idea of expanding space. And I came up with a way to kind of trick my brain into understanding it. Let me tell you about it. So let's say I wanted to find out whether this room were expanding. What would I do? I'd take something like a meter stick, I'd lay it down side by side until I count the number of meter lengths from one end of the room to the other, say it's 10, okay? Then I wait a while and I'd repeat the exercise, and now I do it and it's 11. Okay, so I've just learned that the room seems to be expanding. But there's another possibility, equally compatible with that data. It's possible that instead of the room expanding, the meter stick I'm using is shrinking. You can't tell the two apart. Well, maybe you could. If you could compare that meter stick to something else, like the length of my arm or something, you might notice the meter stick is shrinking. So maybe, instead of the room expanding, everything in the room is shrinking together in unison. So, if a cosmologist tells you space is expanding and you have a hard time picturing that, you could equally well think of everything in the universe as shrinking together in unison, including fundamental constants of nature like the speed of light and the distance between electrons and protons and atoms and things like that. But all of those things shrinking at the same time will be indistinguishable from space itself expanding. All right, moving on. So this is the heart of the Big Bang Theory. Space is expanding, so in the past, any given volume of space was smaller, and since it contained the same amount of matter, it was denser and hotter. So the Big Bang Theory is basically a theory saying that some billions of years ago, our universe was once in a hot and dense state, and it expanded onward to eventually become the universe we see today. That's all we mean when we talk about the Big Bang Theory. I want to make one thing perfectly clear. A lot of us, when we picture the Big Bang, we picture something like a cosmic explosion, some event that took place in space. But that's not what cosmologists mean. The Big Bang was not something that happened in any particular place. It was a state that the entire universe was in 13.8 or so billion years ago. If I say, for example, that a second after the Big Bang, the temperature was 100 billion degrees, I don't mean the temperature at some place in the universe. I mean the temperature throughout the entire universe. Or if I say that 380,000 years after the Big Bang, the first atoms formed, that didn't happen somewhere. That happened everywhere throughout space. The Big Bang wasn't something that took place at one location in space, but it's something that took place throughout the entirety of the universe about 13.8 billion years ago. All right, so let's take a history tour, a cosmic history tour on this timeline of cosmic events. Here I have the Big Bang, the origin of time. You can see a couple of 100 million years or so after the Big Bang, the first stars began to form. We call this cosmic dawn. These first stars were pretty different from the stars we have in our universe today. They were bigger. They didn't have much chemical diversity. They were basically made of hydrogen and helium. Nothing else really existed yet. And because they were so big, they were hot, and they ran out of fuel quickly, exploded quickly. So these were short-lived and volatile stars, but they were important in our universe's development. And then about 9 billion years later, our sun and the planets that make up the solar system formed, all about the same time. Within a pretty short time, geologically speaking, simple life began to emerge on Earth, and evolution began to take its grasp of our ecosystem. And then here we are, 13.8 billion years after the Big Bang, and in roughly 1 pixel on this plot, all of human history takes place. This timeline is fine. There's certainly nothing incorrect about it. But to a cosmologist, they think this is about the most boring way you can plot cosmic history. It's boring because all the best stuff happens right here. Okay? So let's plot the same thing in a different way. Instead of a linear scale, we'll use a logarithmic scale. So power's a 10 in time. This allows us to go back a lot farther and see some of the most important transitions in our early universe's cosmic history. In particular, I'm really excited, and cosmologists in general are really excited about this moment in cosmic history, about 380,000 years after the Big Bang. This was the moment when the first atoms in our universe's history began to form. This transition had everything to do with the temperature of the universe at that time. Today, all of space is filled with a background of light and other radiation that's only about 2.7 degrees above absolute zero. Very chilly universe we live in today. But when the universe was smaller, it was hotter. And about 380,000 years after the Big Bang, all of space was filled with a background of 3,000 degree radiation. That's comparable to the surface temperature of a red-colored star today. Except instead of it being at one place in the universe, it permeated throughout all of space. It turns out this is an important temperature because it's the temperature at which atoms melt. What do I mean by that? So if I took a gas of particles and I put them in a box, gas of atoms, and I slowly heated up those atoms, nothing would happen much until I reached a temperature about 3,000 degrees, at which point the electrons would begin to break off of the atoms. And instead of having a gas of electrically neutral particles, you would have a plasma of electrons and protons and other nuclei. This is critical because whereas a electrically neutral gas of particles you can see through, as this is just like I'm looking at you right now and you're looking at me, there's a gas of electrically neutral particles between us, plasmas are opaque. So prior to this moment in time, the universe was not transparent to light. Trying to shine light through the universe in earlier times would be about the same as trying to shine a flashlight through the earth. It just won't get very far. But here at this moment, suddenly all these electrons and protons become bound together. Our universe becomes transparent, and an enormous amount of light is released into the universe. Here's an image of that sort of transition. On the left, we have helium nuclei, protons, and electrons, all free, and light is just bouncing back and forth like a billiard ball table, not really making it very far at all. And then by the right side of the transition, we have electrically neutral atoms in a configuration that light can easily pass through. Now, I'm a scientist, and if you want to convince me that an event like this really happened, you can't just assert it. You have to provide me with some really compelling observational or empirical evidence. And you might think that would be really hard to do, given how long ago this took place. But in fact, you'd be wrong. The evidence is overwhelming. This is an image taken by something called the Planck satellite of the light that was released into our universe 380,000 years after the Big Bang with the formation of the first atoms. We call this the cosmic microwave background. It's all around us. It's not very bright, but it's all around us. 400 or so photons of light from the Big Bang fill every cubic centimeter of space today. And we can measure it. We measure it a few degrees above absolute zero today. It's cooled a lot since it was released into space. And it has tiny little temperature variations. You can see the pattern of hot and cold spots on this map. And that tells us, basically, what the density variations were like in the early universe. The hot spots are places with less density than average. The cold spots are places with higher density than average at that moment where the first atoms were forming. This is a true treasure trove to cosmologists. This is the single most valuable piece of data we have. All right, so let's go back to our timeline, going back even further. To this point, the first minutes and seconds after the Big Bang. Around then, the temperature of space, of the entire universe, was around 1 billion degrees. That's similar to the temperature you'd find in the core of a massive star, a star much bigger than the sun. And at those temperatures, nuclear fusion can take place efficiently. So you should think of our universe in its first seconds as being an enormous nuclear fusion reactor. It was constantly converting protons and neutrons that were produced in the Big Bang, fusing them together into things like deuterium, helium, lithium, and beryllium. Now, we can calculate using the theory how much of each of these nuclear elements should have been formed in this process. And then we can go out with our telescopes and measure those abundances in various places that we think were primordial. Were created shortly after the Big Bang and not more recently. And when we do those comparisons, we find they match very, very well. We have the right amounts of helium, deuterium, lithium, and beryllium in our universe that match the predictions of the Big Bang theory. So this leaves us quite confident that more or less our universe expanded from roughly that point onward in a way that's approximately the same as our equations and the theory of general relativity and other theories of nuclear physics predict. That's the sort of process, okay. Going back even further, we can go to this point about a millionth of a second or so after the Big Bang. This was the temperature where we think the first protons and neutrons began to form. There's a temperature of about 10 trillion degrees. Prior to this, there were no protons or neutrons. There were only the particles that make up these objects, the things we call quarks, and the particles that hold them together known as gluons. So prior to this point, the universe was filled with a quark-gluon plasma. But at around a millionth of a second after the Big Bang, those quarks began to merge together, congealing into the first protons and neutrons. Now, I think most cosmologists are pretty reasonably sure that something like this happened. It might not have happened exactly like this timeline says, but probably something like that happened. And that's despite the fact that we don't have any way of observing this part of our universe's history. So whereas the formation of the first atoms, we can actually measure that light and be really confident that that happened the way we think. And the first nuclei, we can be pretty confident because we can measure those nuclei out in the universe. Here we can't actually measure anything about what happened in this era. But we can do something to study it all the same. So instead of actually observing that moment in time, what we do is we try to recreate the conditions that were present at that moment of time in laboratory environments using machines we call particle accelerators. This is an image of the world's most powerful particle accelerator. It's called the Large Hadron Collider. It's underneath the city of Geneva, Switzerland, and nearby France. The big circle there shows where the main ring is. It's an underground tunnel, 17 miles in circumference. Around that tunnel, here's an image of the tunnel. There's this beam where we accelerate using powerful magnets protons to almost the speed of light. And when I say almost the speed of light, I mean about 99.999997% of the speed of light. So extremely close to the speed of light. And then at designated places, we take these beams of protons and direct them into each other head-on. We collide the particles together in these devices. They're gymnasium-sized devices consisting of 21st century electronics we call particle detectors. And in those particle detectors, about 600 million times a second, we collide protons into one another and study what comes out. Now, it might not be really obvious why this would be such a great way to study the laws of physics. If I wanted to learn a lot about auto mechanics, I can think of better ways to do it than driving my car into another at the fastest possible speed. That's just not a very good way to learn about most things. But when it comes to the fundamental constituents of matter and energy, Einstein told us something very important. He said E equals mc squared. And what that means is that if we get enough energy in one place at one time, we can create forms of matter with a lot of mass. We can convert that energy E into mass M. So by colliding these protons together, we can make things that don't exist in our universe in any large abundance today, things like top quarks or Higgs bosons, which was discovered at the Large Hadron Collider in 2012, or the top quark, which was discovered at Fermilab in the mid-1990s, and many, many other particle species that are very, very rare today, but that were plentiful in huge abundances in the early universe. So if you go to a point a trillionth of a second after the Big Bang, all of space was filled with a plasma of those sorts of things that we study at the Large Hadron Collider. top quarks, Higgs bosons, W's and Z's, and so on and so on. This is a chart of all of the known fundamental constituents of nature. All of these have been observed at the Large Hadron Collider, and other than the Higgs boson, all of these have been observed at other previous machines as well. A trillionth of a second after the Big Bang, all of these forms of matter and energy were found throughout all of space, constantly coming into and out of existence in rapid succession. So at this point in the talk, you might have the impression that what I'm trying to tell you is that we really understand the first second of our universe's history. That is not the impression I intend to leave you with. We know some things. I mean, we have a pretty good theory, and we're quite confident that from a few seconds after the Big Bang to the present, that theory reasonably well describes how our universe evolved and why it evolved over those times. But that first second, we don't have any way of really directly measuring. And although the Large Hadron Collider tells us a lot about the laws of physics that would have pertained to that first trillionth of a second, there's a lot of room for things to have happened or events to have taken place or forms of matter and energy to have played an important role that we currently don't know about yet. Furthermore, as a cosmologist, I look at some of the puzzles that we face that have come up in the last years and decades that we've really struggled or maybe even outright failed to resolve. And all of those puzzles kind of point back to this first second or so. And they leave me, for one, thinking that the events that took place in that first second might have unfolded in ways very different than you'll find in modern cosmology textbooks. Let me tell you about the puzzles I have in mind. There are 4 of them. The first has to do with the existence of matter. When we take the data that we collect at the Large Hadron Collider and other such experiments, we find that for every form of matter that exists, there always exists a near perfect copy that we call antimatter. So for example, there's the electron. The electron has an antimatter counterpart that we call a positron. They have the same mass, they have all the same characteristics, except whereas the matter version, the electron has a negative electric charge, the positron is positively charged. Quarks have antiquarks, neutrinos have antineutrinos, so on and so forth. Every kind of matter and energy in our universe has a mirror copy of itself, an opposite version of itself in the form of antimatter. Furthermore, one can't create matter without creating alongside it an equal amount of antimatter. And you can't destroy matter without destroying an equal amount of antimatter. In this sense, the fates of matter and antimatter seem closely intertwined. So this is where things get confusing for a cosmologist. If we took what we think we know about the laws of physics, we should conclude that the early universe should have been filled with equal amounts of matter and antimatter. And as space expands and cools, that matter and antimatter should have efficiently destroyed each other, leaving our universe in a state in which there were almost no protons, electrons, or neutrons, and therefore no atoms, and certainly no planets or stars or us. And yet here we are. So we don't know what the resolution to this is. We have a bunch of ideas. Almost every cosmologist has at some point in their career written a paper proposing a way to accomplish this. But we just don't know which one's right. It almost certainly involves laws of physics that we don't know about yet, acting under particularly volatile or turbulent conditions. But we don't know how or when. The second puzzle, again, has to do with matter, but not the kind of matter that takes the form of atoms, but of something else, something that doesn't appreciably radiate, reflect, or absorb light. For lack of a better name, we call this stuff dark matter. So this is an example of an image of a galaxy, our nearest neighbor, the Andromeda galaxy, about 700 kiloparsecs away. When you look at the way in which the stars and gas move around this galaxy, you can estimate, and actually measure pretty accurately, how much mass must be contained in that system, basically by its gravity. In the same way that I can look at the motions of the moons moving around Mars to infer the mass of the planet of Mars. I can weigh Andromeda by looking at the orbits of the outskirts, stars on its outskirts. And when I do that, I find that about 5/6 of its mass can't be accounted for by things like stars and gas and dust. Something else. And this isn't just peculiar to Andromeda. This is true across a wide variety of galaxies we observe, galaxy clusters, even dwarf galaxies and other sorts of systems. Also, when we look at the cosmic microwave background, that light that was released 380,000 years after the Big Bang, and we look at the temperature variations, you can tell from those that there must have been a great deal of dark matter that pulled the matter together to form these galaxies in the first place. And more generally speaking, we can't explain the patterns of galaxies and galaxy clusters we find in our universe unless there's a lot of dark matter that basically provides the scaffolding for the formation of those objects over cosmic history. So we have many different reasons to conclude that dark matter exists and makes up about 5/6 of the total matter in our universe, and yet we have no idea what it is. Now, if you asked me 10 years ago, or you asked most people who worked on dark matter professionally 10 years ago, they probably would have told you that they think the dark matter is likely to consist of things we call WIMPs, weakly interacting massive particles. So these would be sort of like particles like neutrinos, but heavier, okay, and stable. And these particles would have been produced in huge quantities in the Big Bang, and as space expanded, most of them would have been destroyed, leaving only a small abundance behind. But it turns out that that abundance is the right amount to make up the dark matter. That's why we found WIMPs to be so compelling. It was easy to understand how the right amount of dark matter would have been formed in the first millionth of a second or so. But also, if you asked me 10 years ago, I would have told you we know how to build the kind of experiments that should be able to detect WIMPs if they're real. In particular, I skipped these. Okay, sorry. Here we go. We knew how to build these underground dark matter detectors. This is a laboratory in Italy called the Gran Sasso Lab. But experiments like Xenon and DarkSide, Dama, CREST, all of these are dark matter detectors. And these are experiments varying from a few tens of kilograms to several tons of very carefully instrumented high-tech materials and electronics. They're buried underground so that energetic particles from space don't reach them. There's enough Earth between the surface of the planet and the detector to kind of shield them from various kinds of noise. But the dark matter can go right through the Earth. It basically doesn't know it's there. And every once in a while, a dark matter particle will come in and hit an atom in your detector, and you'll be able to see that. WIMPs should be able to be detected by experiments like this. And the experiments have done beautifully. They've exceeded all expectations in terms of technology. They have functioned better than we could have hoped for, and yet no signs of dark matter particles have appeared. So some of us have looked at this new information and said, well, maybe dark matter was produced in some totally different way. It's a different kind of particle, and we have a bunch of different ideas. I don't want to give you the impression that only WIMPs are a possibility. We have many, many other ideas as well. But it's also possible that we've misunderstood the conditions that were present when the dark matter was being formed in that first fraction of a second after the Big Bang. We're not sure. The third puzzle I'll talk about has to do with how the universe has been expanding over its history. So if you took Einstein's equations from his 1915 theory of general relativity, and you said, well, we live in an expanding universe, how can a universe like that evolve over time? There were basically three options. The math said that either the universe could get bigger for a while, reach a maximum size, and then start to contract, ultimately doing something like a Big Bang in reverse, what we call a big crunch. Or maybe it will just get bigger without limit forever. Okay, that's possible. Or there's this intermediate case where it gets bigger and kind of then eventually plateaus in the long run. These were all reasonable possibilities, and it all depended on exactly how much matter there was in the universe. And a lot of the job of cosmologists throughout the 20th century was to try to figure out which of these described our universe. And in the 1990s, we finally had the sort of technology and the kind of telescopes that it would take to resolve the issue once and for all. And when those measurements were made, to our surprise, the answer wasn't A, B, or C, but D, none of the above, a curve that looks more like this. So like I said, to our surprise, the universe wasn't just expanding, it was expanding at a faster and faster rate. You'll note that all of the lines that were predicted by theory were lines in which the rate was slowing down as time went on. That's not what we have since observed. And this is really surprising in the same sense that if I said I'm going to take a cannon, and in that cannon I'm going to fire a cannonball upward, and I say, predict what it will do. Well, if you don't fire it that fast, it will reach a maximum size and come back down. If you fire it fast enough, it will slow down but eventually escape the Earth's gravity, flying off forever. In other words, it will follow one of these three curves. But now let's say I fire my cannon, and the cannonball doesn't just go upward, but it goes upward faster and faster and faster. That's not what cannonballs do. And this line is not what we expected our universe to do. We do have one way to explain it, though. It involves positing a fixed energy density associated with space itself. So what I mean by that is if I took a given cubic meter of space, anywhere in the universe, any time, in any place, I took out all of the particles, all the light, all of the other forms of energy, so it was just pure empty space. If that space still had a certain amount of energy associated with it, it will drive a universe to expand like this in an accelerated fashion. We call that sort of energy dark energy, or sometimes vacuum energy. It means the same thing. And it's the sort of thing that Einstein's theory says is possible, but before the 1990s, we didn't have any good reason to think it was likely to exist. And frankly, we don't have any good way of explaining why it exists, or especially why it exists in the quantity it does today. It is a big open question, and we don't know why our universe started out with that sort of characteristic built into it. The fourth and final puzzle has to do with why our universe on very large scales seems to be so uniform. If I take a telescope and I look as far back in time and space as I can that way, and then I do that way and a whole bunch of different directions, I find basically the same thing. Everywhere I look, it's the same temperature. The kind of patterns of hot and cold spots are the same. And I don't know about you, but if I found a whole bunch of different places, or different things in different places that were all synchronized nearly perfectly with each other, I would assume that somehow they had an opportunity to communicate, to synchronize. So let's say I find a bunch of stopwatches, and they all have been stopped, and they all say 2.1786 seconds. Exactly. I would say, well, this isn't a coincidence. It just isn't a bunch of people stopping stopwatches at random. At some point, these were all brought to the same place, and somebody synchronized them. With our universe, the problem is that even though the different directions show pieces of our universe that look identical or nearly identical, those parts of the universe were never in contact with each other. They're disconnected causally. According to our theory of expanding space, according to Einstein's theory, the part of the universe I can see in that direction and the part I can see in that direction, even traveling at the speed of light, could never have interacted with one another. So it just doesn't make sense that they would have had that opportunity. To explain that in some other puzzles, in the 1980s, physicists started to posit that you could solve this if the very early universe had a special phase, something we call the inflationary phase. A brief moment, very, very shortly after the Big Bang, even earlier than any of the events I talked about in that timeline before. And in that brief moment, space would have expanded extremely rapidly. In something like 10 to the minus 32 seconds, two very nearby particles would have been separated by so much distance they would never have a chance to interact ever again. This has the effect of taking things that were close and synchronized with each other, in equilibrium with each other, and separating them by vast distances, explaining why that part and that part of our universe are so much alike. It also can explain why our universe's geometry is spatially flat, which I haven't talked about, but that's another feature it explains. And it makes a bunch of other predictions. It tells us things about what that light left over from the Big Bang should look like, that cosmic microwave background. Just to throw some words out, I won't define these things, but it predicts you should find a Gaussian and nearly scale invariant spectrum of temperature variations. Well, that's what we found. It makes us think that it's pretty likely that this inflationary era really took place. Something very different than anything Einstein or other early cosmologists might have envisioned. One thing I really personally enjoy about inflation is it seems to go on forever. Once you have a piece of inflating space, little bits and pieces of it stop inflating, and they basically become universes. But other parts of space just keep going, creating more and more patches of space that go on to become things like universes. So if this goes on for a while, you wind up with a situation where you have an extremely large or maybe even infinite number of patches of space that you could call a universe. A multiverse, in that sense, seems to be a natural conclusion, a consequence of the existence of an inflationary phase. So, like I said, I like this in part because I think it's kind of silly to imagine that we don't live in a multiverse. I can imagine all sorts of early human beings imagining that their little piece of the earth was all that existed until they managed to travel somewhere else, learning there were other places, other groups of people, other everything. And then as recently as the Middle Ages, the consensus was Earth was a unique realm, and all the things that we called planets were different sorts of objects made of different stuff and following different laws of physics. Copernicus changed that. He said we're not anything special. We're just one of many planets. All those other things are orbiting the sun just like us. And around the same time, astronomers like Giordano Bruno started to suggest that maybe those bright objects we see in the night sky that we call stars might be the same sort of thing that the sun is, just farther away. And then as recently as the 1920s, astronomers were arguing about whether the Milky Way was the only galaxy, or whether those other blotchy things we saw in our telescopes might be galaxies just farther away. So throughout human history, we seem to have been surprised every time the biggest thing that we know of that we live in doesn't turn out to be unique. I would be personally surprised if our universe turned out to be unique. A multiverse is a very natural thing for me to consider. So, let me back. To give you an idea of how I view the state of cosmology today, I'm going to say a couple of extreme things and then try to bring them together. First of all, I think we have a spectacularly successful theory. For all intents and purposes, the Big Bang theory is correct. Our universe did factually emerge from a hot and dense state over 13.8 billion years, and we understand how and why that happened in exquisite detail, from the first second or so up to the present. I would be as surprised to learn that it didn't play out that way as I would be to learn that the American Civil War never happened. Okay? The evidence is just too overwhelming. These are facts. These are just things we know to be true. So that's one extreme thing. I can stand by that, but it's trying to take a hard position. And then the other extreme thing is that it would not surprise me at all if that first second was extremely different from anything that we currently have envisioned. Laws of physics that we can't even wrap our head around or even guess at yet, forms of matter and energy, if those are even the right words to talk about the things that existed then, that we currently have no inkling of, events that we currently have no idea about. And maybe when we have a new way of thinking about that window of time, these puzzles will all kind of fall into place. Because right now, we don't have a clue how to resolve these four puzzles. When I try to get my colleagues to engage on this sort of question, I like to do it the following way. I ask them, this is usually something I do at the coffee machine. I ask them what they think it would be like to be a physicist in 1904. Can anyone guess why I picked 1904 of all years?
Is that when they said they already knew everything?
Yeah. 1904, in my reading of the history of science, was the high point in the confidence of physicists that they understood their world and the laws that govern it. We had 2 centuries at that point where Newtonian physics just kept working. We discover new stuff. We discover things like electricity, magnetism, and heat, and whatever. And we just kept using Newtonian principles, same ideas that Newton had about force and space and time and mass and energy, and they just keep working. It seems like there's nothing that this can't solve. And they were right to be pretty confident. I mean, when you have a theory that more or less can be applied to problem after problem for 200 years, you would start being pretty confident in it too. But it was also the case that in 1904 there were a few loose ends. Okay, there was the issue of light. So light had been measured to travel at the same speed, no matter what frame of reference you're in. This is very different from other kinds of waves. If I say a water wave's moving at 20 miles an hour, we can all agree that if I got into a boat and moved along with the wave at 10 miles an hour and measured it again, I'd get a different speed. I would find it moving 10 miles an hour. But light didn't work that way. If I move at some speed relative to the speed of light, or if I measure the light in a different frame of reference, I keep getting the same number, 3 times 10 to the 8 meters per second. And no one knew how to explain that. I don't think anyone had any good ideas at all. So we needed some new conception of what light was or how it worked, something that did not fit into the Newtonian paradigm. There was also a problem with the planet's Mercury's orbit. So like all planets, Mercury follows an elliptical orbit, and the orientation of that ellipse, what we call the perihelion, precesses or changes from orbit to orbit. And you can measure, you can predict how fast the perihelion should precess, and you could measure it, and they turned out to not agree exactly, just a little bit off. Over the course of the 1800s, the 19th century, we measured very precisely Mercury's orbit, and it just was slightly different from what Newton's gravitational theory predicted. Some astronomers speculated that maybe there's a little planet out there, something they called Vulcan. That's where Gene Roddenberry got the name. And he said maybe that was tugging on Mercury just a little bit. But they looked and they couldn't find it. So people began to doubt the existence of Vulcan. And no one really knew how to resolve this. Another loose end, I hate to call this a loose end because it's such a big deal, but no one had even the foggiest idea of how the sun got its energy. By this point, by 1904, it was clear that the Earth and the sun were billions of years old. We now know it's about 4.5 billion, but it was clear that they were very, very old. And we didn't know anything that could supply enough energy to make the sun burn the way it does for billions of years. Even if the whole sun were made of some chemical fuel like gasoline or something, it'd run out of fuel in thousands of years. And you could imagine that the sun had been contracting, converting its gravitational potential energy into starlight, but this would last millions of years, not billions. So there was nothing we understood about the laws of physics that could explain why the sun could produce or how the sun could produce so much energy for so long. And fourth, last but not least, we just didn't understand the inner workings of the atom. The models we had for the atoms, the theories we had for how atoms worked, had fatal flaws. Electrons should just crash into the nucleus in a fraction of a second. Atoms shouldn't have been stable. And furthermore, when we measured the kind of light that atoms gave off, they had these peculiar spectral features. They gave off very, very specific frequencies and wavelengths of light. We didn't know why. We didn't have any clue at all. So taken all together, we had an amazing theory, okay? A spectacularly successful theory with a few loose ends. Now, if you surveyed physicists in 1904, I think you would have gotten, the bulk of people would have said, well, yeah, sure, there are loose ends. There are always loose ends. But just like it's always happened before, we're going to keep applying these same Newtonian tools, and we'll figure out how to make sense of them. Just give it a little time. We'll do some more experiments. We'll do some more measurements. All these loose ends will get tied up. And then 1905 happened. Einstein introduced the special theory of relativity and wrote the first paper on the ideas that would eventually become known as quantum mechanics. We now understand that the speed of light is the same in all frames of reference because space and time are not the way that Newton envisioned them. Lengths of space depend on what frame you observe them in. The duration of time between events depends on what frame of reference you make the measurement in. Space and time are not Newtonian. They're relativistic. Okay, they're very different. Also, Einstein's general theory of relativity, which came out of his special theory, would explain Mercury's orbit. Newton's gravitational force is just an approximation. In reality, space, or the phenomenon we call gravity, is a result of a curvature of space and time. Gravity is not a force at all. It's just a manifestation of the shape of space and time. When it comes to things like the sun, where it gets its energy, equals mc squared provides the answer. You can convert a very small fraction of the sun's mass through nuclear fusion, producing enough energy to power the sun for more than 10 billion years. And the inner workings of the atom is a quantum phenomena. That paper in 1905 that posited that photons were in fact particles was the first step towards understanding the atom. All of these things happened not by expanding upon or tying up loose ends associated with the Newtonian paradigm, but by throwing out the Newtonian paradigm and replacing it with something truly new. Cosmologists today, maybe we will resolve the four issues I talked about today by tying up some loose ends. Maybe we'll discover what dark matter is, and we'll make sense of dark energy and understand better how and why inflation took place, and maybe we'll sort out the antimatter-matter asymmetry problem. Maybe that's the case. And a lot of my colleagues would say that's most likely. But I look at this and I think it smells a lot like 1904, and maybe a cosmological paradigm shift is coming. And of course, Thomas Kuhn and the other philosophers of science who talk about paradigm shifts will tell you can never know when's going to happen until it already has. So I'm not here to tell you that one is going to happen. But it does smell a little bit like a paradigm shift coming. And I, for one, hope one comes. That's what I'm cheering for, because it'd be really exciting to live through one. So thanks so much for your attention. I think we'll turn over to a Q&A now. And then when I'm done, I've got a bunch of books over there on the sort of stuff I talked about today. I'd be happy to sign a copy if you were so inclined. So thanks for your attention.
Thank you so much, Dan. That was brilliant. And we do have time for questions. So please just raise your hand and I'll bring you the microphone.
Thank you. That was fascinating.
My pleasure. Thank you.
So the fourth problem, or the fourth puzzle, where particles that went away from each other very quickly, and yet they're uniform wherever you look. That makes me think of, I think it's Bell's theorem. At the quantum level, paired particles can be huge distances apart, but if you act on one, the other one responds. Are those related in any way, or is anybody looking at that?
So what the phenomena you're referring to is quantum entanglement. First, let me just explain for people who might not know what that is, and then I'll answer your question. So this is one of the weird features of quantum physics. Einstein thought it was worrisome. I don't view it as worrisome. I just think it's weird, but lots of nature happens to be weird. I can accept that. But let's say I have some sort of radioactive atom and it decays, and it's going to produce two particles coming in opposite directions. One is going to be spinning clockwise, and the other one counterclockwise, just to balance the angular momentum. But you don't know which one's going to be which. Okay, so two particles come out. You know this one's clockwise, and it means this one's counterclockwise, or vice versa. But quantum mechanics doesn't generally describe things that are in one state at one time. So this one is in what we call a superposition of clockwise and counterclockwise states. And this one is in a superposition of counterclockwise and clockwise states. It's not one or the other. I'm fond of saying it this way. the particles are in clockwise and counterclockwise states at a time, not or. Okay? And then you let them go a long way. And over there I have a detector. It measures one of them. It says, it's clockwise. And then instantly you know that way across the universe, that other particle is counterclockwise. It seems like information traveled through space faster than light. But it turns out that this doesn't actually allow for you to send information faster than light. It's not a paradox at all. It doesn't allow for things like time travel or anything like that. It's just a weirdness of our universe and its laws. In fact, more generally speaking, quantum particles are entangled with any number of particles at any given time. That's just a facet of our universe. So, in the context of inflation, there's a colleague of mine at Fermilab in the University of Chicago named Craig Hogan who's thinking about this very actively. He's talking about signatures you might be able to find in the light from the Big Bang that would show the evidence that parts of the universe were entangled with other parts of the universe during the inflationary era. Frankly, I don't understand the papers enough to give you an opinion on them, but he's a smart guy and he's thinking about these sorts of things. So, yeah, so to answer your question, yes, this is the sort of thing certain cosmologists are actively working
on. Great talk.
Thank you.
Just a question. I have a couple of questions. One is, as I understand it, does inflation mean that things are moving faster than the speed of light?
Yeah.
And how does that sit with you?
So what Einstein's theory says is that things can't move through space faster than light. Okay. That, as far as we know, is a hard and fast rule. If something were to violate that rule, like really paradoxical stuff happens pretty quick. But it doesn't say anything about what space does. So space can grow at any speed at once. In fact, even if you just have kind of steadily expanding space, if you get 2 points in space that are far enough apart from each other, they're moving away from each other faster than light. Just because there's enough space you multiply by the speed. So for example, if we look at something some tens of billions of light years away from us, that will be moving away from us at the speed of light. And that means we can't see anything beyond that horizon. So inflation expanded much, much faster than light, but nothing moved through space faster than light.
Yeah. So that's also why these warp drives work, what you're saying, I think. In other words, they warp space so that you can go faster than the speed of light.
You mean like in the Star Trek universe? Or?
Alcubierre warp drives and stuff like that, yeah.
Okay.
Anyway,
I only know of warp drives in a science fiction context, so I can't comment on any reality of one. But yeah, I mean, wormholes and stuff, like people have talked about as a way to get from here to there faster than light, sure.
My question in those little bubbles of universes is whether inflation is causing these little things, is why don't they collide with one another?
So inflation gets everything very, very far away from everything else. And the same reason our universe isn't colliding with other universes is the same reason why Earth isn't colliding with some planet 10 billion light years from here. It's way too far away. We'll never get there. Even traveling the speed of light, we're not going to collide with any other universe. There's just too much space between us and them.
I'm not sure if my question is in the purview of your talk, but you're a cosmologist, and I've always wanted to ask this question to one. My question is about that, what's often described as the singularity. Mm-hmm. That was the universe, if I understand right, or you can correct me if that's a wrong description. That was the universe at the time of the Big Bang. So if that's correct, what was not singularity at the time of the Big Bang or before the Big Bang?
So,
and how do we know?
So before inflation was introduced into the mainstream of cosmological theories, then if you just took Einstein's equations and ran them backwards, in a finite amount of time you reach a point where space takes on size 0. Okay, that's what we mean by the singularity. And it turns out that work from Stephen Hawking and Roger Penrose and others showed that this was an inevitable consequence of space filled with matter and radiation, that had to be the starting point. And furthermore, it's not that space came into existence then, it's that space and time did. Asking, like, the first event was at t equals 0 at the space-time singularity. Asking what happened before that is like asking where on a map is north of the North Pole. There just isn't anywhere in space-time that is prior to the Big Bang time, space-time singularity. And if there was no time prior to that, there could have been no events and therefore no causes. Space-time is just a closed thing that exists, and one place of it happens to be the edge of it. Now, inflation changes all that. You have a situation where, you kind of truncate that end. You cut off the North Pole, if you will, and you say, well, now a whole bunch of stuff happened in here, and we're not sure what was before that. It's possible that inflation just went on forever. It's possible that it kind of loops around on itself, that after a while, one of the things that inflation creates is just the first thing, and it's just a loop. It's possible that any number of things happened prior to inflation that we're currently not thinking about. And it's possible that the old Hawking-Penrose space-time singularity took place prior to that. All of those things are possible, and probably things I have no idea even to think about yet.
What do you expect to learn from the James Webb Telescope?
So there are a bunch of new telescopes on the horizon that I'm excited about. James Webb is one of them. You can think of James Webb as the successor to Hubble, and also whereas Hubble was primarily an optical telescope, James Webb will primarily be an infrared telescope. One of the things James Webb will do is those first stars that formed a couple 100 million years after the Big Bang, it will measure those with much greater precision. Directly image them really for the first time. With the James Webb Telescope, we'll be able to measure the current expansion rate of the universe much, much more accurately and without certain systematic errors that we worry about. That's important because right now we have kind of two different ways to measure the expansion rate of our current universe, and they don't agree. And that might be evidence that there were things in the first few 100,000 years of our universe's history that contributed to the way the universe expanded that we currently don't know about, or could be one of the groups is doing it wrong. James Webb should settle that, or at least could help to settle that. And then in general, like I can think of any number of things James Webb will help us to do that I wouldn't put under the purview of cosmology, but just other kinds of astrophysics. People studying planets and other solar systems are excited about James Webb. People doing stellar evolution, people doing galaxy formation and evolution. All of these branches of astronomy and astrophysics will benefit from James Webb.
Quantum theory predicts that there's the lowest energy state of the electromagnetic field is something that's pervasive in space that you can't get rid of. And that energy density, is enormous, 10 to the 100th joules per meter squared, which, and this seems unphysical, but that's a hard prediction. What's your thought on that?
So, yeah, I mean, if you take quantum field theory, which is the modern version of quantum physics, and just calculate what all the particles spontaneously coming into and out of space, at every moment of every second of every instant of time, you can make an estimate for what that energy density should be, and it's way too big. It's 10 to the 120 times bigger than the actual measured density of dark energy. I'm pretty sure we're just thinking about this wrong. Well, okay, there are two possibilities. One is we don't know how to calculate this. The theory is not equipped to do this in the same way that Newtonian physics wasn't equipped to talk about black holes. Okay, and maybe someday we'll have a theory in which this question makes sense. Or maybe, and I like this other idea too, probably even more, It's an idea that was put forth by the Nobel Prize-winning physicist Steve Weinberg back in 1987. Now, bear in mind, this was before dark energy was discovered. He said, well, my calculations of dark energy are way too big, 10 to the 120 times too big. We know that in a world like that, life couldn't exist because space would expand so fast that you'd never have any stars or planets or galaxies. That's an uninhabitable universe. But what if there's a multiverse, he said, and there are a practically infinite number, maybe infinite number of universes, and all of them have different amounts of dark energy in them. We would expect to find ourselves living in a universe with approximately the maximum amount of dark energy consistent with the emergence of life. And he calculated how big that should be. 10 years later, we measure the amount of dark energy in our universe. It's about that number, within a stone's throw. So it's possible that we live in a very, very rare universe, and that the vast majority of places in the multiverse don't have life in them. And we just happen to be in one that can support life because, of course, by definition, we are in a place that can support life.
Why didn't the early universe collapse into a black hole because of the density? And then also, did any early events see the universe with black holes that, like, are supermassive black holes that galaxies formed around?
So I happen to be pretty immersed in a project right now where we're considering black holes in the early universe. That's sort of my I got to the Wheaton area about an hour early today. So from a coffee shop, I did some black hole in the early universe calculations. So this is definitely on the tip of my brain. But the early universe would have been very, very uniform. And black holes don't form when the density is uniform. It's kind of analogous to if there's the same amount of stuff everywhere, gravity doesn't pull you anywhere, right? It pulls everything in all directions, and you don't actually form a black hole. Now, it's possible that inflation may have left the early universe with some density fluctuations, and they might have formed black holes. But they wouldn't have been black holes that made up the whole universe. They would have been very, very small. And in fact, if you do a naive estimate of how big you expect those black holes to be, they're like somewhere between the size of this thing in a car. That's in terms of mass, somewhere from grams to tons. That's a sort of natural range. And all of those black holes will evaporate through a process called Hawking radiation, or Hawking evaporation, in the first second after the Big Bang. So those could have done a bunch of cool things, though, in that window of time that I think is so mysterious. Maybe they made the dark matter. Maybe they generated more matter than antimatter somehow in their evaporation. So they might have played a role in these sorts of puzzles. That's why I'm thinking about them. As far as supermassive black holes go, we do know that all, or at least almost all, galaxies harbor a multi-million solar mass black hole at its core. We more or less understand why they're there. I mean, dark matter and other matter will collapse and form black holes pretty early, and then black holes merge with other black holes and so on and so forth, making successively larger ones. But there are some issues that we don't understand. We have observed some black holes in the form of quasars at quite some time ago, and we don't think there should have been any black holes quite that big that early, and people are actively trying to investigate how they might have formed that early and what we might be getting wrong.
Okay, I'm afraid to ask this question.
Don't be
I'm
afraid.
really slow, and I know it's going to sound really stupid, but
I doubt it.
people usually don't talk about this. So I'm having a really hard time wrapping my brain around this idea of a multiverse, okay, because I'm just starting to feel comfortable with the idea of galaxies.
Okay.
Okay? And so my understanding, and I don't know if it's part of my religious background or something, that I've got a mental block or what it is, or maybe just I'm stupid, I don't know. But so my understanding of universe being countless, beyond comprehension amount of galaxies. And what they're in is something called the universe. Now you're saying there's multi-universes of this. Can you explain more what a multi-universe is?
Yeah, so the word universe is used differently by different people, okay? So let me define my terms first, okay? So some people say the unity of everything that exists is the universe. And then by definitions, there's not a multiverse, okay? I'm using the word slightly differently. I say that any two things that even in principle, if they can interact with each other, they're in the same universe, okay? So that means that anything that, if it sent me a signal right now at the speed of light, straight towards me, if it can get to me ever, then I'll call it in my universe. And that means my universe is a giant circle of space, sphere of space, tens of billions of light years in diameter. Beyond that, we're surrounded by this cosmic horizon, and I can't influence, interact with, or otherwise experience or learn about anything beyond that. It's forever separated from me. So that's what I mean by a universe. And unless you think space really ends at that boundary, which of course we can never prove it doesn't, but it would be weird if it did, I think, then you think that there's another universe here and another universe here and so on and so forth. And if inflation took place, and not only that, but then there would be, vast numbers of universes, maybe with different laws of physics and different kinds of particles and different kinds of things and different kinds of whatever, scattered across a vast amount of space. So that's kind of what I have in mind when I talk about multiverses. Physicists also use the word multiverse to mean different things, but that's what I'm talking about. And yeah, I mean, our piece of causally connected space within our horizon contains hundreds of millions of galaxies. But I would be shocked if that's all there is to existence.
You mentioned multiverse. It just popped up the question of dimensions. And I want to see what you thought about, because, in the spiritual conversation, dimensions come up a lot. So I just was wondering how that played into your physics background.
Do you mean dimensions of space? Or do you mean something else when you say dimensions?
However you perceive it, I guess, because I don't even know how I perceive it. It's just a word that's popular and like, okay, cool.
So when physicists talk about dimensions, we say, well, we seem to live in a four-dimensional space-time, okay? So I have, this, and this, plus the dimension of time. Einstein says they get all kind of blurred together, but four-dimensional space-time. But there could be fifth, sixth, seventh, et cetera, dimensions. There has to be some reason why we don't perceive them very easily. Maybe the particles that we experience, like electrons, only move in some subset of the dimensions. It'd kind of be like, imagine that on the surface of a table, you have something like a magnet that's stuck to that table. And it can move, along that table, but it's not capable of moving up and down. Maybe the particles that we interact with and we're made of only move along that table of three-dimensional space, and there are other dimensions that, it's not capable of moving through. It's also possible there are other dimensions and they're wrapped up in little tiny circles, so small that particles of the sort of energy we interact with normally can't fit in those dimensions. The wavelength of a particle is inversely proportional to its energy, so you might have to have a very, very high energy particle before the wavelength is small enough to fit in that little loop. That's the sort of thing string theorists talk about a lot. It's also possible that, and then if you go to really extreme circumstances, like the first 10 to the minus 43 seconds after a space-time singularity, like right immediately after the Big Bang, it's what it even means to talk about a dimension of space starts to be a little bit fuzzy. There are these ideas in string theory and other kinds of formal physics now where you can write down a theory that describes a bunch of particles and energy in a certain number of dimensions. And then you can write down a different theory in a different number of dimensions that describes space and time. And you can show that mathematically these are the same theory. So you might have a theory that's 4-dimensional if you look at it in one way and 5-dimensional if you look at it in another. And you might really look one of those two ways until you look at that universe and the conditions shortly after its Big Bang, in which case it might take on a different kind of dimensionality, making you rethink the structure of the question altogether. Very speculative stuff, though. So.
Why is it impossible to go faster than light? And the other question I have, is it possible to travel back and forth through time?
Good. So I'm going forward through time right now. So are you. Backwards, much harder. But okay, I'll go back to that. So if I have an object and I want to accelerate it, Einstein's special theory of relativity tells me how much energy it will take for me to get it at some speed or some other speed. And it turns out that to get to exactly the speed of light takes an infinite amount of energy. The more energy I give something, the closer it gets to the speed of light, but it never exceeds the speed of light. It just gets closer. I can go from 99% to 99.9% to 99.99%, et cetera, et cetera, et cetera. But it would literally take an infinite amount of energy to acquire the speed of light. So for that reason, you just practically can't exceed it. But there's another good reason, too. Einstein's theory can be used to show that if there is an object moving faster than the speed of light, then in some other frame of reference, that object is moving backwards through time. And if something is moving backwards through time, then I can use that to send signals backwards. Maybe I use a signal, I send it back and arrange for my grandfather to be killed before he meets my grandmother. And then I'm never born, so I don't send the signal back because I'm not there. And then my grandfather does meet my grandmother and I am born. And I do send the signal back, and now you see the logical paradoxes that ensue. So in order to have a logically self-consistent universe, there has to be no backwards time travel, and that seems to require nothing travels faster than light. Back to the moving through time thing, I think we can all agree we're moving forward in time. And you can, furthermore, you can change the rate at which you move forward in time by traveling at great speeds. There's an illustration of the special theory of relativity called the twin paradox, where you take two people born at the same time, twins if you like. One gets in a spacecraft, it travels at nearly the speed of light, it goes to some distant star system and back. And in that trip, as far as the moving astronaut is concerned, only a few years pass, okay? They only ate a few years worth of food. They only watched a few years worth of DVDs. They only slept a few years worth of nights. All the clocks on their spaceship said only a few years pass. But when they return, hundreds of years of human history have played out. The clocks that are moving at nearly the speed of light pass through time differently, more quickly, if you will, than stationary clocks. And this is something we've measured. This isn't science fiction. This is something we just know is true. So if you can build something to carry your body at nearly the speed of light, you can move into the future as well. Moving backwards, I think, just can't happen for the logical problems and the grandfather paradoxes and stuff I mentioned before.
Yeah, but here's another thing. You say
wait. One more question.
You say that the person who's flying away and going on the trip, he apparently ages more slowly than the one who doesn't go anywhere. But how do you determine which person is moving? Because in order to determine movement, that's all relative. Maybe the guy who's staying still is the one who's moving. He's the one.
So there are these things called inertial frames. And the rule of thumb, the way you can figure out which one is moving in the sense that we're talking about now, is one of them feels the effects of acceleration, deceleration when they turn around. So if you're traveling near the speed of light and you put your brakes on, you feel that deceleration, and then you feel the acceleration while you speed up going back home. So there is a difference. It's, and you wouldn't know that by using special relativity alone. You need the general theory to differentiate between the frames of reference. But they're not the same. They're not the same. Because one, you feel acceleration, and one you don't.
I find that I find that when I consider the cosmos, and particularly space and time, that it has an influence on my perspective on life and on my personal philosophy and spirituality. And I was wondering, with your vocation, what impact what you're studying and learning has on your day-to-day outlook on life, and what this kind of thinking might have for us all.
So I certainly can't speak for all cosmologists. Any two cosmologists will have a different outlook on life and their meaning in their universe. And even if you asked me at different points in my life and career, I might have given you different answers. But if I'm answering right now for myself and today, I would say that the more I've studied about the universe, the less I think there's anything about the universe that tells me what's meaningful. I don't know of anything I've learned about the universe, how it's evolved, how it began, where it's going, that gives me any reason to feel any particular way about it. All the meaning that I find in the universe is stuff that human beings have imposed on it. That doesn't mean it's not real, doesn't mean it's not valuable, but it's something that comes from us, not something that comes from the inanimate material or space and time. It's something that comes from our brains and our experiences and our emotions. But that's the best place to draw meaning from, I think. I think that's where all the real magic of human experience is. I love members of my family and my friends in very, very real ways. Cosmology has nothing to do with that. Discovering the nature of dark matter or knowing how matter and antimatter emerge differently from the Big Bang won't change that at all. I will feel just as strong about that the day after we've settled those puzzles as I do now.
If you imagine that the Big Bang starts in a very small region and all this stuff is created at the same time, and then expands to create the universe, can you say that because it's all created in the same process, everything is entangled in the quantum mechanical sense? And then as this expands, you have a huge entangled system. And I don't know if this is a theorem or not, but can a system make a measurement on itself to end its entanglement? I'm not sure. Let's say it can't. If it can't, then that means that the whole universe is, is entangled in some sense.
Yeah, so I thought a little bit about this, but I don't feel I can give you a particularly good answer. I mean, I think you asked before about entanglement and inflation. And I do know that real cosmologists are thinking about signs of quantum entanglement associated with inflation. For things to become entangled, they have to be causally connected to each other at some point. So it would take something like inflation to do that. But that seems to be coherent to me. But you know what? I'm not sure it super matters. It could, in the sense that you might look for certain kinds of correlations and patterns in the cosmic microwave background. But if I'm, some atoms in my body are quantum entangled with some atoms somewhere else on the Earth, I don't know that leads to anything weird or anything problematic. I think that's okay.
Hello.
Hey.
So is the picture that we're looking at more or less a visual of the multiverses? And are you saying that the multiverses do exist? And on one hand, I want to ask, how do they get created? But is this like where you mentioned when the Big Bang happened, not just in one spot, but when it happened, it formed all of these multiverses at the same time?
So I want to make one thing clear. This is just an artist's impression, whatever. This is not meant to reflect a physically realistic picture of the multiverse. I just think it looks cool. That's why I use it. But here's the sort of the generation of a multiverse through inflation might look like to me. So imagine there's like a Big Bang, a space-time singularity, and some very, very short period of time later, that space starts to expand exponentially and super, super rapidly. Every once in a while, because the laws of quantum mechanics say that things don't happen predictably, some places will stop inflating before others do. So now imagine there's a patch of space that decides it's going to stop inflating. It expands, stops inflating, and then it just expands normally, evolving through all the stages I described on these timelines. That's a universe for all intents and purposes. For my use of the word, that's a universe. But that bigger inflating space, not just the patch that stopped, but the rest of it continues to do that. Maybe it gets 10 times bigger in volume, and then another patch of it stops inflating, making another universe. And then the rest of it continues to inflate. And now it stems off 10 more universes, and then 100 more, and then 1,000 more, and then 1 billion more, and then I don't see any reason to think that ever ends. In fact, the math in most inflationary theory says it doesn't. It just happens forever, generating universes without limit. I hope that helps.
Dan, did you say that the matter and antimatter in the universe have to be equal?
So they're not.
They're not.
Okay. I mean, because we live in a universe that has an awful lot of matter in it and very little antimatter. So, but nothing we've learned about the laws of physics can explain that yet. If we just took the information we know from particle accelerators, and from that information tried to deduce what should have happened in the Big Bang, we would conclude that the universe should have contained equal amounts of both, and they both should have destroyed each other, leaving us with neither. So back in the 60s, a Soviet physicist, Andrei Sakharov, he didn't know how this happened, but he deduced that at least 3 conditions must have been met in order to explain the survival of matter over the victory of matter over antimatter. One, there has to be some kind of interaction out there that allows the net amount of matter minus antimatter to change. Okay? We've never seen something like that, but he said some sort of interaction like that has to exist in nature. Secondly, there has to be some sort of, in that interaction, it has to have like a bias. It's not just enough to change the amount of matter, but it has to preferentially change it in favor of matter against antimatter. We call that sort of bias CP violation, charge parity violation. And then thirdly, these interactions that are biased in favor of matter over antimatter and that change the net amount of matter relative to antimatter have to have taken place in particularly volatile conditions. Maybe during some sort of phase transition in the early universe, or maybe in some other sort of non-smooth, non-smooth and non-steady environment. All 3 of those have to have happened. And I think I said this before, but just about every cosmologist has at some point in their career written a paper saying, here's a way it might have happened. And I've done it too. And the problem is we have any number of hypotheses in very little way to tell to deduce which one's likely to be true. Right now I'm thinking about black holes as an origin. You could imagine I can solve all 3 of these problems if I say that there were black holes in the early universe. They weren't in equilibrium with the bath, so I get my 3rd condition for free. And now I'm going to imagine that they radiate away very, very heavy particles that we can't see in particle accelerators, and that those make only matter when they decay. That solves 1, 2, and 3 all at once. But would I bet that it's right? No, because there are another 1,000 theories that are equally justified.
And related to that, just so that maybe matter and antimatter may be equal, even though it seems to be contrary to the fact of existence of matter. There is a Buddhist scientist who made this comment, and I'd just like to get your reaction to it. Because people always say about the existence of the universe, and he, where you can't get something from nothing. And he said, that is true. You cannot get something from nothing, but you can get nothing from nothing. And based on his Buddhist understanding of emptiness, and which is kind of esoteric, I know, but this idea that maybe what we perceive as matter is actually empty. And what are your thoughts on that?
So when physicists use words like matter, they have very specific kinds of meaning in mind. And I don't know how to talk about like saying something like maybe matter is emptiness. That means some of those words are being used in a different way than I've been trained to use those words. And it's fine. Words oftentimes have many meanings, and like I'm sure that those words in that order mean something to that monk, but I don't know what they are. I don't know what it means, so I can't really comment on it very precisely. I know what I mean by the word emptiness, and I know what I mean by the word matter, and they're not the same thing. But I suspect he's trying to say something deeper than I currently understand with those words in that order.
Deeper than all of us probably understand. Thank you so much, Dan.
Sure.
I know some of you may still have questions, and I know I hogged the last two questions. I'm sorry. I rarely ask questions, but I couldn't resist. Really appreciate you coming here this evening, and really brilliant presentation and thought-provoking, and just opening our minds to these mysteries and yet questions that are really meaningful. Dan's book is available there at the Edge of Time, and if you've been inspired by his presentation and his just the brilliant thought that he brings, have a look at the book, get one, get it signed. Maybe you never know in the future, that book may be worth a great deal. So thank you, Dan, a hand of appreciation.
Thank you all.
Also, just two announcements before we finish, all three. Tomorrow evening, we invite you to relax and bathe in a sound healing with Tibetan and crystal bowls being presented by Yolanda Lozano. And we do these sound bowl vibrational kind of gong baths once in a while, really relaxing, soothing and healing. And if you are free, please come. If you'd like to register, go to our website and just scroll down under events, and there you can register for it. Also on Thursday, John Robertson, who's our Tai Chi teacher, is offering a workshop on Tai Chi, Qi Gong, Shibashi, which is a set of gentle flowing exercise. It's a routine that one can learn in one day. And it's supposed to be extremely beneficial for health and well-being and vitality. If you're interested in participating in that workshop, if you're interested in Tai Chi, Qigong, even if you haven't practiced any, this is just a small set of exercises that he will be teaching. If you're interested in joining that, please do register tomorrow. Registration is quite low as it stands now, and unless we do get quite a number of new registrations, we may cancel the workshop. So don't just show up on Saturday expecting that the workshop is happening if you don't register first. Last thing, Thursday next week, we will have Richard Smalley, who is the editor of the Quest magazine of the Theosophical Society, author of many books. and often speaker here. He'll be talking on Atlantis, then and now. Thank you all for coming. Please come again. Enjoy some refreshments. Get a book.